In number theory, we learned that math can apply to many interesting things from cards to calendars to music and art. So in elementary school, you probably learned to draw a star by starting with a circle with 5, adding a line from the first point to the second point, fourth point, until you came back to the starting point to get a finished star. Now this star was pretty straightforward, but what if you wanted to draw a star with a different number of points? How many stars can you make? Can you make different stars with the same number of points? To start figuring this out, let's set up some definitions. From now on, we're going to say that stars need to be symmetric, they can't be regular polygons, and you need to be able to draw them without picking up your pencil. If it doesn't meet these requirements, we won't consider it a star. We'll call the number of points a star has n, so for our kindergarten star, n equals 5. We'll call the number of points you move along the circle with each edge d. For this star, d equals 2. We'll also define two functions. S of n gives the total number of unique n-pointed stars. S of d in n determines whether there is a valid n-pointed star using d as the distance between points. If we can figure out how to calculate these two functions, we will be able to answer all of our questions about stars. To start out, we'll test some values of n and d and see what we can learn. For 5-pointed stars, we already know that d equals 2 works. Next, we'll test d equals 1. Lines. Our result is a pentagon, which is not a star, so d equals 1 does not work. In fact, if we tried any other n value, we still would have gotten a regular n-gon, so d equals 1 will never work. Let's try d equals 3. We get a star, and interestingly enough, it's the same star that we got for d equals 2. So we'll say that 3 is valid for 5-pointed stars, but we need to take note of this non-uniqueness because it is important later when we're counting the number of stars that we can draw. Finally, we'll test d equals 4. So we see that this is not a star, and in fact, it's the same shape we got for d equals 1. So for 5-pointed stars, d equals 2 and d equals 3 generate valid stars, and d equals 3 and d equals 4 are not unique. So we can learn a couple of things from the 5-pointed stars. First, we learned that d equals 1 will never work because it will go through all the points in order until it gets back to the starting point at the end of the first loop. This generates a regular polygon, which is not a star according to our definition. We also learned that d and negative d mod n generate the same shape because the circle we are using to generate is symmetric. So since d equals 2 worked, d equals 3 worked as well. And since d equals 1 didn't work, d equals 4 didn't work either. So there are at most n over 2 unique shapes because half of them are duplicates of each other. Of these unique shapes, we already know that d equals plus or minus 1 doesn't work, so the number of possible unique n-pointed stars can't be more than n over 2 minus 1. So now we have some interesting restrictions and some upper bounds, but we still don't have a definitive answer, so let's try a different value of n. For 6-pointed stars, we already know that d equals 1 won't work, which means that d equals 5 won't work either. We also know that we won't have to test d equals 4 because it will be equivalent to d equals 2. So let's start by testing d equals 2. Okay, this is a new result. Instead of reaching all the points to create a 6-pointed shape, this drawing went back to the starting point and repeated after only reaching 3 points. Clearly, this is a valid 6-pointed star. So now we know that both d equals 2 and d equals 4 won't work. All that remains is to test d equals 3. So to use d equals 3, we draw a line to the third point, and then immediately back to the starting point, then back to the third point, and so on indefinitely, never generating even a 6-pointed shape, much less a 6-pointed star. So after testing all the different values, we discovered that there is no way to generate a 6-pointed star. So we learned a couple more things from n equals 6. First, we learned that d equals n over 2 will never work because we get a line, not a star. Next, we learned that even if d is greater than 1 and less than n over 2, there are still cases where it doesn't generate a valid star. We don't know how to define these cases yet, but we know that they exist because we found one with n equals 6 and d equals 2. We can develop a couple of hypotheses about what those cases are. First, 6 is a composite number, while 5 was prime, so it's possible that there are no stars with a composite number of points. We could also hypothesize that both n and d contribute to whether or not there's a valid star. 6 is divisible by 2, so that's a possible reason why that shape didn't work. 6 and 2 are also not relatively prime, so that is yet another possible reason. To test our hypotheses, we'll look at 10-pointed stars. We already know that 1, 5, and 9 are invalid values for D. 10 is composite, so if our first hypothesis is correct, there will be no valid stars at all. 10 is divisible by 2 and 5, so if our second hypothesis is correct, 2 will be invalid, but 3 and 4 will work. 10 is relatively prime to 3, so if our third hypothesis is correct, 3 will be valid, but 2 and 4 will be invalid. First, let's check 2. We expect not to get a valid star, so if we do get one, we know that all of our hypotheses are wrong. And in fact, we get a pentagon, which is not a star, nor even 10-pointed. So 2 is not valid, which we were expecting. Next, 3. If it's valid, we know that there can be stars with a composite number of points. And we did get a valid star. So our first hypothesis was disproved. There can be stars with a composite number of points. Finally, we'll test n equals 4. If we get a valid 10-pointed star, it would support the second hypothesis that you get a valid star as n isn't divisible by d. If we don't get a valid star, it would support our third hypothesis that you get a valid star as long as n and d are relatively prime. The result is a star, but it's not a 10-pointed star, so 4 doesn't work. So after testing, we can see that there is one unique 10-pointed star. This supports our hypothesis that you get a valid star if n and d are relatively prime and d is not plus or minus 1. To prove our hypothesis, we must first remember that a valid star reaches all n points using exactly n lines. We'll number the points along the circle from 0 to n minus 1. We'll call c the number of the last point reached, and x the number of lines drawn. Since we move by d points with every line, c is congruent to dx mod n. The drawing has to reach every point, so the congruence for c must have a solution for every possible value of c. This congruence has a solution if and only if c is divisible by the greatest common denominator of d and n. And since 1 is a possible value for c, the greatest common denominator of d and n must be 1. So, this means that d and n must be relatively prime in order for the drawing to reach every point on the circle. Also, as we discovered earlier, d can't be congruent to plus or minus 1 or it would generate a regular n-gon, not a star. So now we know which values of d are valid, but we still need a way to calculate the number of valid values. We'll define a function called phi of n, which is the number of numbers less than n that are relatively prime to n. All of these relatively prime numbers, except for 1 and negative 1, generate valid n-pointed stars. So there are phi of n minus 2 possible values for d that generate valid n-pointed stars. However, we already learned that the star generated by d is the same as the one generated by n minus d. So half the valid stars are duplicates. Therefore, the total number of unique n-pointed stars is half of phi of n minus 1. We've figured out the answer to our original questions, but we still need to know how to calculate phi of n. If n is prime, then phi of n is n minus 1, because every number less than n is relatively prime to n. If n is a power of a prime number p, then all the numbers less than n are relatively prime to n except for the multiples of p. So, phi of p to the k is p to the k minus 1 times p minus 1. It is interesting to note that for both prime numbers and powers of primes, if p is the prime factor of n, then phi of n is n times 1 minus 1 over p. We're going to use this fact later, so remember it. The other case we need to analyze is the product of two relatively prime numbers. We'll create two sets of numbers, a and b, where a is the set of numbers mod q that are relatively prime to q, and b is the set of numbers mod p that are relatively prime to p. Every number that is relatively prime to n is also relatively prime to both p and q, so we can pick any value from set A and any value from set B and use the Chinese remainder theorem to solve for a value that is relatively prime to n. Therefore, phi of n is the size of set A times the size of set B, or phi of q times phi of p. Now we are ready to get a general formula for phi of n. Every positive integer can be expressed as a product of powers of primes. These prime factors are all relatively prime to each other, so to calculate phi of n, we find the phi function of the powers of its factors and multiply the results together. Using the formula we discovered earlier for the phi function of powers of primes, we can rearrange this expression to learn that phi of n is n times the product of 1 minus 1 over each of its factors. Now let's try an example where n equals 100. This would be really hard to do by hand. To start out, we need to know phi of 100, which is 100 times 1 minus 1 half times 1 minus 1 fifth, which is 40. So the number of unique 100-pointed stars is phi of 100 over 2 minus 1. So there are 19 unique 100-pointed stars. The values of d for these stars are all the numbers between 2 and 49 that are not divisible by 2 or 5. So 3, 7, 9, etc. Finally, here's a graph showing the number of unique n-pointed stars for n up to 1,000. This top line here is generated by all of the prime numbers because they maximize phi of n. The bottom of the graph is numbers with many prime factors.